Hello, this video is to briefly introduce my master thesis. The goal is to locate the safe landing sites for the drone in the unknown environment where the GPS signal can be denied through the onboard camera and the geometrical based algorithm. There are three metrics are used to define the safe landing site. The first one is the slope of the side should be small enough, and the second one is there should be enough room to support the drone feet, and the third one is there should be no collision between the drone and the terrain. With these metrics, we can locate the possible safe landing site in any terrain model, and the geometrical base model is built on PCL, as known as the point cloud library, with C++ programming. As you can see here, this is one of the terrain model from online resources. This is based on the coordinate of this data point is based on the word frame, and here shown as the map frame, and above the map frame there's a camera frame which represent the onboard camera of the drone, and that also indicate the initial position of the drone. And as you can see, there are some colorful region here, and that I will explain later. The first step is to meet the slope condition. So we need to extract the region where have the small slope, and to do this we can estimate the normal vector of the point cloud surface, and the result is shown as here. And as you can see, the extracted region have all of them have a very small slope, which means it's relative flat, and that's why it is a good terrain region to be the safe landing site of the drone. And hence we can apply the voxelization technique to find the center of the potential landing site on the projection of these point cloud data, and the result is shown as here. Yes, so here is the top view of the projection of the point cloud data, and the red dots represent the potential landing site center. And as you may notice that there is some red dots, for example this one, that's not on the gray region, and that is because of the property of the voxelization technique. For example, if my voxel size is a 2 by 2 size, and then in this case the data points of the gray shade region is mainly distributed away from the center of the voxel, like here, 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 and here. And the centroid of all these data points within the voxel is here, and that's also the place where the gray data point is not exist, and that's the reason why the center of the potential landing site is not on the terrain data. Okay, once we got the center of the potential landing site, we can also compute the corresponding drone feet position on the projection of the original point cloud model. It's shown here. Yes, it's shown here. So you can see that the blue dots cluster um, represent the drone fit position, and hence there are, as you can see, there are 10 potential landing sites are found here, which is this one, this one, this one, this one, and so on and so forth. And you may also notice that there is some there is some center of the potential landing site um, which does not contain the blue dots cluster around. And take this as the example. That is because the geometrical model cannot find enough room to support all the drone fit. For example, this one approximately in this location, there is no enough room to support the drone fit. Hence, the algorithm evaluate this position does not satisfy the second matrix to locate the drone, and hence this one and that one. So in this case, we have the center of the potential landing site and the corresponding drone fit position of uh, the corresponding center on the projection of the original point cloud model, and then we can find the corresponding drone fit position on the original point cloud model, which is this one. As you can see, the blue dot region represent the drone fit position on the original point cloud model, and the pink dot cluster represent the drone span, which is estimated by plane fitting on the blue dot, which is the drone fit position, which is the point on the drone fit location. And the blue dot is the propeller span, and the blue dots, the propeller span and the drone span are used to check if the drone will collide with the terrain. And here, as you can see, there are 10 potential landing sites are found. However, only 3 of them are the safe landing site, which is this one, and this one. And for these 4 potential landing sites, as you can see, there is no way they can satisfy the slope condition, meaning that these 4 potential landing sites have a large slope value, and which is not safe for the drone to land. And here, these 3, you may see there's a black dots here, and here, and that's the dots can cause the collision between the drone and the terrain, and hence these 3 are not safe for the drone to land because of the collision, and only these 3 landing sites are safe for the drone to land. The advantage of the geometrical based model is that it has a really fast computational speed, and hence it can be applied on the real-time application. But the downside of such model is that for the same set of the hyperparameters, it cannot guarantee as good as the performance shown here um, in the other terrain, meaning that for different terrain model, it may require to further tune the hyperparameters to give a same level performance. So that's basically my master thesis. Thank you for listening and watching.